some of the people that make SRI really interesting and great. So if you have the chance to talk to them, they're got lots of interesting ideas. And with that, I'll let Melinda start.
Okay. Well, thank you for that, Adam. So as Adam mentioned, I'm Melinda Gervasio, and the work I'll be presenting today is joint work with Karen Myers at the Artificial Intelligence Center at SRI. And I'll be talking about our work on leveraging AI planning models to adapt sequential pattern mining for procedure learning. So the motivation behind this work is the following. So humans are quite adept at learning from observation. So apprentices learn a lot of their craft by watching masters at work. New hires can learn a lot about their job and about organizational practices by shadowing more experienced professionals as they go about accomplishing various tasks in the workplace. And even nonverbal children can learn how to solve simple puzzles or assemble structures or play with a new toy by watching their playmates in action. So most of the time, of course, learning isn't done purely by observation. There's often instruction or demonstration too. So the craftsman demonstrates specific skills and explains why it's important to pay attention to certain things. The experienced administrator generally outlines the steps in a process before teaching a trainee how to do it. And we know that with children, there's often a lot of trial and error and learning from experience. But even without these additional sources of information, we're able to watch other people perform tasks and to piece together the steps that are required to accomplish that task. So we can determine how the steps go together, what actions serve as prerequisites to others, what actions are superfluous or even erroneous, and so on. And we can abstract our observations to be able to learn a general plan that we can apply in other similar situations to accomplish the same task. Now, the idea of learning generalized plans or procedures is nothing new, of course. In the AI planning community, for example, there's a large body of work in this area. Started way back almost 50 years ago with the concept of macro operators developed in strips. So macro operators, basically they serve to compile away the search that's involved in generating a plan so that you have initially a sequence of actions that accomplish a goal from a particular initial state. By generalizing this and abstracting that into this macro operator, planning and execution can then be reduced to instantiating this macro op in a new situation. So since this seminal work, of course, there's been a lot of extensions to macro op learning, including learning iterative and recursive plans, learning partially ordered plans, learning HTNs, conditional plans, and so on. Our motivation here is the same. We want to learn general plans that apply in many different situations. However, this prior work is predominantly about learning from traces of agent behavior. So that is the learning algorithm is generally given as input, sequences of actions or states and actions that are examples of plans that achieve the goal from particular initial conditions. So these can be problem-solving traces of an automated planner or traces of the agent's behavior or demonstrations of an expert. But in all cases, they're typically well-delineated sequences from which a general plan or procedure needs to be learned. So again, in contrast, rather, our target here is an event log. Specifically, we're interested in finding automatable procedures from logs of user actions. So these event logs already exist today in the form of transactional databases or, say, instrumentation logs from websites, other computer software. And with advances in NLP and image processing technology, we'll probably soon have event logs in the forms of actions or activities that are inferred or recognized from, say, video footage or audio transcripts or chat logs. So we're interested in capturing or learning automatable procedures from these logs, but these logs serve many different purposes, such as discovering simple patterns or capturing actual workflows, perhaps comparing them to idealized workflows for conformance checking, performing various data analytics, and so on. So they're not built basically for learning procedures, and so they present a number of challenges. And basically learning procedures from these event logs are different from learning from traces of agent behavior in a number of ways. So first, right, the procedures often involve multiple agents. So imagine a typical travel reimbursement process, right? It requires different individuals to collect and upload receipts, file the report, audit, sign, issue a check, finally. Second, the logs can include external events that are outside the control of the human or even the system. So for example, customers initiating a service call or periodic system events, maintenance or processing events. Third, even with a single agent, there will often be multiple interleaved tasks that are being pursued at the same time. So think how often you find yourself multitasking at your computer, right? Looking up flight information while reading email and writing a report. And fourth, the action sequences in the logs can often be incomplete or suboptimal. So processes can be abandoned for any number of reasons, or they may involve some trial and error before finally getting on track. And finally, event logs are noisy. In general, a lot noisier than traces of agent behavior simply because of the volume and the types of information being logged. And many of these will be irrelevant from a procedure automation perspective. Now, the field of sequential pattern mining has been investigating the problem of finding sequential patterns for many years now, so a few decades. So in the data mining community, for example, the concept of market basket analysis has been used to try and mine customer transaction databases to discover things like, people who buy wine often also buy olives and cheese, or people who rent Star Wars or stream Star Wars these days often rent Return of the Jedi afterwards. Or people who buy a new iPhone also often buy a new iPad within a year. So in that field, people use sequential pattern mining to develop various marketing strategies. Similar problems have also been explored in other areas, such as bioinformatics, where sequence mining is used to discover patterns that have some significant biological function or purpose, such as they call these motifs. In all these cases, the problem really boils down to finding repeated, very frequent sequences of events. And the field often deals with very large databases, so a lot of the focus has been on developing highly efficient algorithms for finding these patterns quickly, under certain constraints like minimum pattern size or finding only maximal patterns and so on. So it made sense to us to use this approach as a starting point for learning procedures, that is generalized action sequences from event logs. However, much of the power in sequential mining algorithms comes from their simplicity. So they tend to treat events as being atomic entities. So so for example, looking at these 4 examples of a sequence here. It's a remove followed by an add. Sequential pattern mining typically does not look at the parameters to action. So from their perspective, these would be examples of exactly the same procedure, or remove followed by an add. But if you look at what they actually do, you can see that they're quite different, right? So for the first one, it's really about moving one file from one folder to another, whereas for the last one, right, it's moving one folder from one folder to another, and the second one is, removing a file and adding a folder. So they're very different, and these distinctions are not captured by traditional sequential pattern mining. So to address this particular problem, we use a an algorithm we developed which basically folds in unification and variabilization into the sequential pattern mining. Another problem is that, and this is related to the first, is that there are no semantics to the events that are typically addressed by sequential pattern mining techniques. So the example on the left, for example, is how market basket analysis is typically performed. All they care about is, the products a customer buys, which they can track by assigning an ID to each product and then operating over those IDs. So they don't care about the types of the products, their properties, whether they were bought with cash or credit or anything else about them other than ID. And similarly with biological sequence discovery, which often operates over simple alphabets. Of course, this is not the case with actions, right? Actions have a purpose, they operate over entities, they have constraints on their use, and we execute them to affect changes in the world. And this is the focus of this work. So specifically, we wanted to see whether we could use planning knowledge to provide semantics to patterns. So I will now be describing the experiments we performed and the approach we took to trying to do this. So first, I'll talk about sort of the baseline performance of applying state-of-the-art but off-the-shelf sequential pattern mining techniques to mining event logs for automatable procedures. And then I'll discuss our approach to developing filtering heuristics based on action models. And then I'll describe a couple of experiments with both a noise-free and noisy data sets, and finally some summary and conclusions. So first, we'll look at the baseline performance. That is the straight application of an off-the-shelf pattern mining algorithm to an event log. So we use for our experiments the large bank transaction process data set. So this is taken from various event logs that are being maintained by an IEEE task force on process mining. So it supports process mining research in general, and it's also used for their annual Business Process Intelligence Challenge. So the large bank transaction process dataset is one of these synthetic event logs. They were generated by the P3net process model that you see here, and don't worry about the details. This is just to provide context for the sub-process that we worked on. So in particular, we worked on this sub-process here, which you can see in more detail here. It's the authentication sub-process. And these labels here might not mean much to you, but basically the way to read this is that the squares are actions and the circles are essentially decision points. And so the way to read this graph is that all the branches coming out of a square or action correspond to actions that can be traversed in any order. And if you go from sort of the green blocks to the red blocks, any path from a green block to a red block, again, going through all the intermediate squares in any order, will lead you to what we consider a gold standard or a ground truth procedure. So counting up all these paths from a green to a red square will give us a total of 28 ground truth procedures, which are basically the procedures that we would like our procedure mining algorithm to discover. So the bank transaction dataset comes with a log of 2,000 noise-free transactions. But since we're interested in learning from much smaller datasets, what we did was we just randomly chose 100 of those. And that's our noise-free dataset. And then we also created 3 different noisy data sets. So one of them had redundant actions. Basically, we did this by going through each action in the log and then repeating it with some probability, in this case, 0.1. We also created a noisy data set with extraneous actions. Similarly, we insert a random action with some probability, and then there was a final noisy data set with both types of actions. So to provide the baseline performance, we applied a state-of-the-art off-the-shelf sequential pattern mining algorithm called CM-SPAM. And our goal was really to utilize existing pattern mining algorithms. So in some sense, the algorithm we use here doesn't matter too much. And in fact, we tried others and the performance was similar. But basically what you see here is that sequence mining finds many, many more candidates than there are true procedures. So there are only 28 real procedures, but it finds almost an order of magnitude more candidates than that. So recall is perfect in at least a couple of the cases, but precision is very poor, at 12% at most in the noise-free case. We also look at the F scores, and in particular, we thought the F 0.5 score would be useful because it weights precision twice as much as recall. And basically, we think that we'd be willing to give up finding a few procedures if we can get a higher hit rate with the procedures found. So here again, we see that the F scores are fairly poor when you just apply off-the-shelf pattern mining to event logs. So then this is basically what we want to do. So as we saw, right, if you take a log of user actions and you apply sequence mining, you get very, very many frequent patterns. So what if we could apply some sort of filtering so that we get a much smaller set, and then we could feed that to our procedure learning algorithms and actually learn useful procedures. So we decided to look at developing filtering techniques using AI planning action models, in particular the use of inputs and outputs and preconditions and effects to characterize actions. So specifically, we want to borrow two concepts from the action modeling work. So first is the concept of preconditions and effects. So here's one action from the bank transaction domain represented as a PDDL or PDDL action schema. So for those who haven't heard of this, it's basically an action, the planning representation that borrows from strips and ADL. And it was originally developed to provide a common language for the inaugural international planning competition at ICAPS. So it's a language for representing not just a domain model, that is action definitions, but also planning problem specifications. And it's since been extended to encompass more complex concepts, but for our purposes, really, what we're interested in are the use of parameters, preconditions, and effects. So in this simple example here, we see that the finish authentication action has two parameters, a sender and an authentication ID. To be applicable, it has to be the case that the sender is being authenticated and that the sender has already been registered. And the action, when executed, has the effect that the sender will no longer be in the process of being authenticated and instead will be authenticated. So this is just a simple example of the kinds of information that we'd be able to capture with an action model such as this one. The second concept we borrow is one used more in information-centric domains, where basically the data or the information that flows from one action to the next is a primary concept. So as data flows through the system, it undergoes various transformation, processing, fusing, and other operations. So the outputs of actions typically serve as inputs to downstream actions. And actions are captured in terms of their inputs and outputs. So here, for example, we see the start authentication action represented in terms of its inputs and outputs, and we see that it takes as input a sender and generates as output a unique ID. So what we use is a hybrid model that characterizes actions in terms of preconditions, effects, inputs, and outputs. So using these action models, then we designed two types of filters. The first set that we show here are the candidate filters. So given a candidate frequent sequence discovered by pattern mining, we use these filters to drop less promising candidates according to some heuristic. So we have, a precondition filter that looks at whether actions have unsatisfied or unsatisfiable preconditions. We have a start filter that discards candidates that do not start with an action that begins a process. So we have metadata on, the I guess, conditions that are known to be the starts of processes and the ends of processes. Similarly, with the finalized filter, we look at whether a candidate ends with an action that completes a process. The complete filter is a combination of those two, and I'll talk about it a little bit more later. And the branch filter discards a candidate that does not start with a recognized branching action. And again, we have metadata that indicates what actions are sort of branching actions. So for example, the precondition filter works this way. It looks at the sequence, and if the sequence contains any action that has an unsatisfied precondition, we simply discard the candidate. So here, for example, if we require that a customer be validated, then if there is a previous action that has that effect, we keep that candidate, but if there isn't one, then we discard that candidate. So the simple right, so this is just a simple example of the precondition filter. Another example is the complete filter, and basically the heuristic here is that if any process is started, we want to make sure that it's also ended. So here, if we start the background check on an applicant, we want to make sure that we complete that background check. Otherwise, we discard the candidate because it's unlikely to yield a useful procedure. So candidate filters are one type of filter. The second are what we call action filters. And here, rather than eliminating entire candidate sequences, we want to try and discard actions within a sequence. So these are designed primarily to handle noise, and they serve mostly to clean up the noise within a discovered pattern. So again, we have three filters: a contribution filter that discards actions that basically serve no purpose as far as we can tell in the sequence, a duplicate filter that discards immediate repeated actions under the assumption that these are likely to be redundant or irrelevant, and a gap filter that allows for noise by ignoring up to a certain number of intervening actions. So here's the contribution filter in a little bit more detail. Basically, it looks at whether any of the actions are, the outputs are used by succeeding actions. If they are, we keep the action. Otherwise, we take out the action from the candidate sequence. And then finally, we have combination filters that just look at various combinations of these filters applied in a certain sequence. So given all our filters, then we ran sequence mining again with the filters on the noise-free and noisy datasets, and here were the results. So on the noise-free dataset, we see that basically all the filters result in improved precision, so highlighted in red in the precision column. Most of them improved it by almost 50%, going from 12% the baseline case to 18% in the filtered case. Although the branch filter did lose, basically its recall fell by quite a bit because it failed to find or discover some of the procedures. And in general, the combinations of filters performed well. Or performed the best. The results with the noisy data sets were consistent with this. So basically, again, all the filters result in improved precision and F-scores with some decrease in recall. Now, the action filters that were designed precisely to eliminate noise did what they were supposed to do, with the exception of the gap filter, which, as you can see here, generated so many candidates that precision just fell quite a bit, as did the F-scores. And in thinking about this some more in retrospect, that makes sense because the gap filter is basically one of the most popular techniques used in sequence mining, and it's really designed to try and find patterns even in the presence of noise. So we thought it would make sense to use here, but it really has the opposite effect for procedure learning, where it finds so many more candidates that it greatly lowers the signal to noise ratio, which is exactly the opposite of what we wanted to do. So the results with the other noisy data sets were similar, so I won't go through them here. But basically now in summary, right, I think our conclusion is that a little knowledge can go a long way. So standard sequential pattern mining techniques, as we showed, discover a large number of irrelevant or useless action sequences. They're really not procedures. But we can use action model-based filters, that is, by utilizing the semantics provided by action models, we can eliminate many of these irrelevant sequences. So with the exception of the gap filter, which again, we realize now that probably was not a good use of the gap filter. It results in greatly improved precision, right? So from 12 to an average of 16% in the noise-free case and 10 to 14 in the extraneous noise case. In particular, combinations of filters are very effective. However, filters do lose some relevant sequences, although the drop-in recall is fairly low. So we think this is a worthwhile trade-off. However, it remains an open question whether, a 1 in 5 hit rate, that is, we have a 20% precision at best, right? Is this good enough for practical use? So then just to end with some future work, so we'd like to look at experimenting with smaller data sets. And in fact, so the whole impetus behind this work was actually a system where we expect to get such event logs from which we are going to try and learn procedures, but the data sets we're going to get are probably much smaller and involve more complex procedures. So we want to experiment with that. We want to look at the use of additional heuristics to improve the precision further. Also look at other uses of the action model, such as generating explanations for discovered procedures so that it's not such a black box. And finally, perform the last step of the vision slide I presented earlier, where we take the filtered patterns and integrate them with our procedure learning algorithms. So thank you very much.